Okie doke. Welcome back to the Rust 0 to 100 series. We're about on the 0 to 100 scale, about 70% there. We got 6-ish more chapters to go, so give yourself a big old pat on the back for getting this far. Arnold wants to congratulate you as well. As a quick recap, we've covered 2 smart pointers at this point, the box type. So we got box with type T, and then we also covered RC with type T. Box takes in some value and holds it on the heap. RC acts the same way, except it remains valid even after the original owner goes out of scope, like we just went over in the last video. We can edit the existing value within the box through our dereference operator. So if we had some, just as a recap, let's say we have some box B equals box new, and we have 100 in there, and we want to print out, if I can type, our box. We can do that through the dereference operator, and then we can edit our box value through, the reference operator here, and then the deref operator here. We can edit the value on the heap or within the box, like so, and then print it out again. Again, this should be a recap at this point, but I could do cargo run. And indeed, we have updated our heap value from 100 to 50. We never changed what address B pointed to here, but we did change the value held at address B from 100 to 50. We're going to introduce a third smart pointer today, the RefCell. RefCell kind of acts like a box, except it allows, Arnold just jumped up on me, 1 second. I like having Arnold in the room, but sometimes becomes a little bit too much, so you gotta boot the cat out. But anywho, we're introducing RefCell today. And like I was saying, it acts kind of like a box, except it allows us to mutate the data inside it, even if the owner is immutable. So we'll go over a quick example. I'll just comment this out, and just for reference sake. And we're gonna declare a new RefCell with RC equals RefCell, and then we do have to bring it into scope with the standard cell RefCell right there. RefCell new, and we're gonna throw in a value 100. And as you might notice, RC by itself is not mutable, but we can get a mutable reference to it. Let mute RC ref equal RC.borrow mute. We can then, with this mutable reference, dereference it, RC ref equals 50, and then we can debug. Actually, I'm going to debug this RC ref instead of RC. And this is going to make sense in just a minute, but just to show that we're indeed updating the value, RC ref is equal to 50 instead of 100. What we're doing is something like this. So we're first declaring our RefCell itself. And remember, RefCell is just a smart pointer, right? So it's just a reference with some fancy metadata going on. And we have an immutable reference to RC, so we can't change what RefCell this RC points to, but we're pointing to a single RefCell, which again holds our value. In this case, T is 100. It's an I32, but we're holding the value 100 here. So we're holding the value 100. We're passing the value 100 here. And what we're doing with borrow mute, we're getting access to this value that's inside the RefCell. So we're getting a mutable reference inside of this immutable RefCell, and we got a mutable RefCell to 100. And with that mutable reference, we did RC, we dereferenced it. We went back inside here, and we got a pointer to the memory address where 100 resides. And we went ahead and did RC ref equals 50 with our mutable reference. So I'll just make this perfectly clear that our mutable reference is this RC ref right here. And we just updated the value 100 to be 50 with this pointer inside of the RefCell. What we're essentially doing with this whole kind of operation here of getting a mutable reference, updating it, what we're doing is moving our ownership restrictions from compile time to runtime. So what I mean by that is, technically we could get an immutable borrow of RC after our mutable borrow, like so. We could do something like let RC immute ref equal RC.borrow. And this just gets an immutable reference, so works like borrow mute, except we can't do, it wouldn't make sense to put mute here because we're not able to update it. It's an immutable reference like we've gone over in ownership before. And then I could try printing out this RC immute ref, and I'm gonna do cargo check real quick. Cargo check. Now I'm just gonna get rid of our diagram for now, but I'm gonna go ahead and do cargo check. And as you can see, we don't get any errors. The compiler doesn't get mad at us, but we did just break ownership rules of Rust. As a recap, with normal references, we can borrow a mutable reference to some value, but if we do so, we can't have any other references to the same value. So just to make sure we're on the same page, if we did something like let mute n equal 5, and then let m mute n ref, a mutable reference to n, it's going to equal a mutable reference to n. And if we tried to do a immutable reference, so just immute n reference equals to n, and then update our mutable reference to something like 10, and then debug our mutable reference and our immutable reference, and then I do cargo check again. Now the compiler is going to get mad at us, even though we did essentially the same thing that we did right here. If you need a refresher of why this doesn't work, I'd recommend checking out chapter 4.2 of the textbook again, but this is illegal code and so is this, but the compiler isn't catching that. We just wrote the same logic with our RefCell and the compiler didn't get mad. We created a value 5, borrowed it mutably, borrowed it again immutably, updated it to 10, and tried to print out both references. Now let's delete this example so our code will compile. And again, I'll run cargo check. Everything's fine and dandy, and I'll try doing cargo run. And what happened is our program panicked. What we have essentially done is move our ownership checks from, again, compile time to runtime. We broke the rules of ownership. That is, the Rust compiler will let us compile our code even though we have both a mutable and an immutable reference to our 100 value, but RefCell is going to panic when it sees that we have both a mutable and immutable reference to this 100 value. I'll just say that one more time. Rust allows us to compile our code with both mutable and immutable references, but panics when our program tries to actually do this at runtime. And the RefCell sees, hey, we have a mutable reference. We just tried borrowing it again. And we already have a mutable reference, so let's go ahead and panic. Why on earth would we want to be able to do something like this? It really just boils down to this. It's a workaround. It's a hack. RefCell is a workaround when we're otherwise forced to use immutable references. With RefCell, we are basically telling the rest compiler, trust me, pinky promise that we aren't holding a mutable reference with one or more other references at the same time. Trust me on this. That's all we're saying with RefCell. That's it. We'll just go over another example to kind of nail this point home. Let's say we're using some library that defines a messenger trait. The messenger has one job to send a message, and we'll say it was defined like this. So we had a trait, messenger, and it has a send method on it that takes a reference to self, and also a message, which is a string slice. Let's also define a limit tracker, which holds a messenger and the current number of messages sent and the maximum number of messages that can be sent. So I'll go ahead and define that. Pub struct limit tracker. It's going to hold a lifetime A because we want this to live just as long as our messenger. So lifetime A, and then we're going to take a type T, where T must be a messenger. And we're going to have a messenger, which is our, again, our limit tracker can only live as long as our messenger. So as soon as our messenger reference becomes invalid, so will our limit tracker. So a lifetime of A to messenger T, and then we have a value of uSize and a maximum value of uSize. Finally, we'll create a constructor for our limit tracker, and so that will look like we're going to implement for limit tracker, and we need to declare the lifetime A, type T for limit tracker, and we're just passing those back in. If I can type, and we're going to say where T is a messenger, and we're just using where, the where keyword in syntax instead of defining it up here like we went in previous video. We could have done that, but we're just trying to make this a little bit shorter. So we're going to now define our implementation. We're going to define our constructor here. So we're going to make it public, function new, messenger, and that's going to have the lifetime A, and it's going to be of type T, and we're going to pass in a max uSize. And all this is going to do is return a limit tracker with a lifetime A, type T. And what we're just going to do is pass in these values, messenger, value 0. Oh, and that's another thing about Rust, is that if we have keys that are the same name as the value, we can go ahead and do without our colon here. And last but not least, we're going to add a set value method, which is going to update our value and sends warning messages if we've reached our, getting close to our maximum number of messages, or if we've exceeded our maximum number of messages. So I'll go pub func set value, and we're going to have a mutable reference to self, value of uSize, and we're going to set our value to value, and we're going to let our percentage of max going to be self.value as a 64-bit floating point, divided by our max as a 64, F64, if I can type. And then if our percentage of max is greater than 1, then we're going to send an error, self.messenger.send error. You are over your quota. Oh no, so sad. You can't send any more messages. Else if percentage of max is greater than or equal to 90%, 0.9, Then we're going to do the same thing and say urgent. You're almost at your quota, 90%. I know this is kind of boring stuff right now, but we're almost there. Else, if percentage of max is at 75%, then we're gonna send warning over 75% usage. Okay, so this makes sense at this point. Now let's say we want to define a couple of tests for our messenger. We want to test our messenger logic out with a mock messenger. This mock messenger will implement the messenger trait, but it'll also hold a list of its own sent messages for testing purposes. So I'll go ahead and let me actually yoink this out into a library real quick so that we can effectively run tests. So like with our testing video, we're going to create a new test module. We're going to first configure that to be test, mod tests. We're going to just bring everything into scope. And we're going to define within our test. And again, think that this, or imagine this all comes from an external crate that we're using, right? So we'll say that we imported our external crate for our test and we want to make a mock messenger. So I'll say struct mock messenger in our tests. It's going to have a bunch of sent messages. And then we'll say we'll implement messenger for our mock messenger. Well, first of all, we're going to define a constructor. We're just going to say mock messenger with 0 sent messages, or an empty vector of sent messages. And then finally, we're going to implement the messenger trait for mock messenger. And we're going to send self and a message with a string slice, just like our send method calls for on the messenger trait. But this is where we're going to run into a problem. We want to do something like this: self.sent messages.push. We want to push in a new string from our messages, or from our message that we just passed in. We can't do that. Phooey. I'll go ahead and just add our the rest of our test here. All it does is goes ahead and tries the 75% out. But this is a situation you might run into where you're implementing something like our send method here calls for an immutable reference to self and a string slice of message. And as we can see up here, that's exactly what our trait is. And that's where RefCell comes in. It's a hack. That's what it is. Another situation where this might come up is maybe we do have access to, or we made this trait ourselves, like this isn't from an external trait, but our mock messenger is the only kind of messenger that needs to modify self, like it's an edge case. In both cases, whether this is from an external crate or we just don't need a mutable reference to self except for a very special use case, then that's where RefCells come to the rescue. So what we'll do is we'll go down to our mock messenger here, and we're going to update this. Pause the video real quick and see if you can think of what we were going to do to our sent messages. And again, we can define the RefCell to be immutable, but we can still mutate the values at runtime as long as we're not violating the rules of ownership. So what we're going to do is going to wrap this in a RefCell. So now we're not mutating anything from self. We're getting a mutable, even though self is still immutable, we're going to call borrow mute and get a mutable reference to this vector, even though RefCell itself is immutable. So I'll go ahead and update our sent messages to be a RefCell. And what we're going to do is self.sentMessages.borrowMute. And now we're reaching into our cell and getting a mutable reference to it and pushing to it, even though self itself is an immutable reference. We got a mutable reference of a vector and push to it. So I'll go ahead and do cargo test on our smart pointers. Oh no, what did I do? The compiler is going to be super friendly to me and tell you, hey dummy, you're trying to get the length of a RefCell, which doesn't have that method. Instead, you want to get the vector from inside the RefCell, and so we can do that with an immutable borrow. I'll go ahead and cargo test again. As we can see, we got one passed. Whoop-de-doo. Again, I want to make it really clear that the rules of ownership still apply, so we could try to do something like let mute or sent messages equals this, and then sent messages dot push, and of course this has got to be mutable because it's a mutable reference. Then we can't do something like this. We can't have a second mutable reference or even a immutable reference at the same time. If I try running this, it's going to panic. RefCell already borrowed. Now here comes the fun part. We can combine our reference counter RC with the RefCell so that a value can have multiple owners, and those owners can mutate the value that they hold as long as the owners themselves or the strong references are not mutating the value at the same time. So we'll go back to our graph example. So we defined a node on a graph like this. We're going to implement derive the debug trait here. And we're going to define our node again, and we're going to say it contains a value this time. Yes, Arnold, it's going to be a car this time instead of an I-32, so that we can have keep track of our nodes A, B, C, D a little bit better. And then we're going to define, like we had before, a vector of nodes, and those nodes can be RC types, because RC means that we can hold multiple strong references to those nodes, right? Just like we did in the last video. And I just went ahead and took our create graph function from our last video and did exactly the same thing. So just in this case, we have B, C, and A as our values for the nodes. And just as a recap, each node in the graph is allowed to have strong references to other nodes in the graph, and that's why we're able to return A and still have references to B and C, and how B can point to C as well as A in this case. And the nodes remain valid in memory even after create graph returns and we only have ownership of A. Now let's say we want the ability to modify the children of our node. That is, we have, from our create graph function, we currently have A pointing to B, and then A pointing to C, and B pointing to C as well. Let's say we want to add a fourth node to this graph D after we've created the initial graph, so that we have something like this where A is pointed to D and so is C pointed to D. How can we do that when we only have complete ownership of A at this point? We can absolutely do that by modifying our node struct so that we're able to modify the children or what other nodes that each node should point to. So I'm going to go back here and we're going to be modifying our node type here. Pause the video real quick and see if you can figure out what we need to do to the node type in order to have a mutable vector of nodes. In our case, the best way to do this would be to wrap our entire vector of RC nodes inside of a RefCell. So we're going to do RefCell vec RC node. So this is a lot of nested types right here, and of course I need to actually import or bring into scope. We're going to do something like this, right? If we did something else, or like there's a couple of other ways like we might have thought to do this. We might have thought of doing something like nodes is a vector of ref cells, which are RC nodes. And so if we did something like that, we're allowing ourselves to change what each element in vec points to, but we aren't allowing ourselves to mutate vec itself, so we can't push or pop or otherwise reassign our vector. And we might have also thought to have done something like nodes vec RC ref cell node. And if we did that, we were giving ourselves permission to change the contents of a child node, but we can't change what our current node points to. If that seems a little confusing, pause the video and try to visualize what we're doing with these definitions of node. So since we want to be able to edit our list or our collection or our vector of child nodes, we're going to go with our first implementation here. I'll now go ahead and just quickly update our create graph so that it reflects having our ref cells in here instead of just straight up vecs. Okay, finally we can enjoy the fruits of our labor and edit our graph. So let's go ahead and create a node D and add it to our graph. So again, we're going to start out with A, B, and C, and then we're going to add D to our graph like so. So we'll go ahead and node, or let D equal node value D, and we're not going to have it have any children, so I'm going to say just ref cell new of an empty vec, and we're going to let A equal create graph. And what we're going to do at this point is we're going to debug and just see what our graph of A looks like. Do cargo run, and let's decipher this a little bit. So we have our node A, and our nodes is going to be a ref cell, and our value of our ref cell is this. So we have nodes B, and B points to C, and then we also have just C by itself in here as well. So what we're going to do at this point is we're going to do let mutable our A nodes going to be equal to our A dot nodes dot borrow mutably, and then we're going to push to our A nodes RC clone of D. What did I do wrong? Oh, duh. Yeah, we need to wrap this in a RC. There we go. And then we're going to grab our C node. So we're going to say let C equals A dot nodes. Or sorry, A nodes. and that we're just going to grab it through the second value within our vector, right? Because we have A and we have B, and then our second value is C down here, right? So we're going to grab our second value, and we want it to be a reference. We can't just nab it, right? So I'll go ahead and, what did I do wrong again? Oh yes, right curly. And I'm doing a reference here because otherwise we would dereference it through this, and that would be trying to move the node C into this literal value like so. And again, the compiler will let us know and be friendly with us. So we're going to go ahead and get a reference to C like so. And we're going to get a mutable reference to the nodes that C has like so. And then we're going to push D to our C nodes, right? Now that's all fine and dandy, but maybe we want to debug our new graph. We want to see what it looks like, right? So we would think about doing something like debug at A again, but as you might expect, this is not going to work. We get, borrowed. What's happening here is because our second debug statement is trying to borrow A nodes and C nodes when it recursively calls the debug trait on it. So instead of panicking, the debug trait actually is a little bit kinder to us because we already have borrowed A and C here mutably. It instead just says, oh, it's borrowed, and does that instead of panicking. So again, debug just says, oops, this value is already borrowed, so we can't print it. So to fix this, we can naturally put this in its own scope, like that. And this basically drops A nodes and C nodes, the references to them, outside of this scope, and we can then debug A like so. And as you can see, we now have our complete graph here. So we have A that points to B, which points to C, and then A also, or C also points to D right here, but then also A points to, what did I do here? We pointed to C, oh, yes, it's confusing to look at. This is within our B to C right here, but we also have our A to D down here. So that's this reference, just proving that we have that. We could have also, instead of declaring its own little scope here, we could have done standard mem drop like we talked about in the other video. So standard mem drop, we could have dropped A nodes, and we could have dropped C nodes as well. We could have done that, and I'll go ahead and, oh, why can't I do that? Because, silly me, I had the order reversed. We need to drop C before A, obviously, like so. But we could have done this as well. And as you can see, we print out everything just the same way, but it looks a little bit cleaner instead of calling this drop function to instead put this all in its own scope, and then A nodes and C nodes are automatically dropped here. And that's a wrap for this video. So in a nutshell, we went over how the RefCell smart pointer allows for what's called interior immutability of the value that the RefCell contains. In other words, we will go ahead and pull it up. We're able to, again, mutate the value within inside a RefCell, even though RefCell can be immutable. And we can generate both mutable and immutable references to the value it contains through the borrow and borrow mute methods. So we also have, as we briefly talked about, borrow mute here. Or just borrow, sorry. Like so. And yeah, hope you learned a lot, and I'll see you in the next one. I'll make some exercises for this video as well.